AI Dropout and Stochastic Techniques Deep Dive. How Senior Engineers Master Randomness as a Training Tool in Modern AI Systems. Welcome back to Agentic AI World. I'm your host, and this is your daily interview prep, sharp, technical, and built for engineers who want to stand out. Today we're going deep on dropout and stochastic techniques. If you've ever been asked in an interview, why does your model generalize? Or how do you handle overfitting at scale? This episode is exactly what you need. Let's start with the core question. What is dropout? Dropout is a regularization technique introduced in 2014 by Srivastava, Hinton, and colleagues. The idea is deceptively simple. During each forward pass in training, randomly set a fraction of neuron activations to 0. That fraction is called the dropout rate, typically between 0.2 and 0.5. At inference time, you turn dropout off, but you scale the remaining weights, usually by multiplying by 1 minus the dropout rate, so the expected value of output stays consistent. Why does this help? Because it forces the network to not rely on any single neuron. Each neuron has to learn something useful on its own, independent of its neighbors. The result is a more robust, generalizable model. A common interview analogy. Imagine training a team where, randomly, some members don't show up each day. Every person has to be capable of doing their job independently. The team that trains this way is far more resilient than one where everyone is codependent. Now let's go deeper. The technical intuition. Dropout is often described as implicit ensemble learning. Every time you apply dropout, you're effectively training a different subnetwork. With a network of n neurons and dropout rate p, you're sampling from an exponential number of possible subnetworks, roughly 2 to the power of n. At inference, using the full network with scaled weights approximates averaging across all those subnetworks. This is called Monte Carlo Dropout when you explicitly keep dropout on at test time and run multiple forward passes to get a distribution of outputs. That's actually a lightweight form of Bayesian approximation. It gives you uncertainty estimates, not just point predictions. Senior engineers use this in production when you need to know not just what the model predicts, but how confident it is. Now let's talk about the variance, because in interviews, knowing the variance signals depth. Standard dropout drops individual neurons randomly. Spatial dropout, used in convolutional neural networks, drops entire feature maps. This makes sense because neighboring pixels in a feature map are highly correlated. Dropping individual values doesn't break those correlations. Dropping entire channels forces the network to learn from truly independent representations. DropConnect, proposed by One et al., takes a different approach. Instead of zeroing out activations, it randomly zeroes out individual weights in the weight matrix. It's more fine-grained than dropout and can be more effective in some architectures. Alpha dropout is designed for networks using CELU activations, a self-normalizing activation function. Standard dropout breaks the self-normalizing property, so alpha dropout preserves the mean and variance of inputs after dropping, keeping the normalization intact. And then there's stochastic depth, a technique used in very deep networks like ResNets. Instead of dropping neurons, you drop entire residual layers during training, with survival probability increasing for layers closer to the input. This dramatically speeds up training of very deep networks without hurting final performance. Let's get into the practical engineering decisions you'd face in production. When should you use dropout? Primarily in fully connected layers of classification heads, language model heads, and encoder-decoder architectures. In modern transformer architectures like BERT and GPT, dropout is applied to attention weights and feed-forward sublayers, typically with a rate of 0.1. When should you not use dropout? In batch-normalized layers, things get complicated. Batch normalization and dropout interact poorly. The shifting statistics from dropout create a mismatch between training and inference distributions, a phenomenon called variance shift. In practice, if you're using BatchNorm heavily, you often skip dropout or apply it only after the BatchNorm layers. This is one of the reasons layer norm, used in transformers, plays nicer with dropout. For very large language models, GPT, 4 scale, and above, dropout rates are often set very low or even disabled entirely during the main pre-training phase and applied only during fine-tuning. At that scale, the sheer data volume provides its own regularization. Now let's talk about the stochastic techniques family more broadly, because interviewers love to test whether you can connect related ideas. DropBlock extends spatial dropout for structured data. Instead of dropping individual activations, it drops contiguous regions. This is especially effective for image models where local features are spatially correlated. Cutout is a data augmentation version of the same idea. You mask out random rectangular sections of input images during training. It forces the model to use global context rather than relying on local patches. Mixup is another stochastic technique worth knowing. It creates synthetic training examples by linearly interpolating between two real examples and their labels. It makes decision boundaries smoother and improves calibration. Label smoothing replaces hard 0-1 labels with soft distributions. For example, 0.9 for the true class and 0.1 spread across others. It prevents overconfidence and is a form of regularization applied at the loss level rather than the network level. Let's hit the interview questions directly. Explain Dropout and why it works. The key is to go beyond. It prevents overfitting. Talk about ensemble learning, co-adaptation prevention, and the implicit regularization effect. What's the difference between dropout at training time and inference time? Training, randomly zero neurons and train with raw activations. Inference, no zeroing, but scale activations by the keep probability. Some frameworks implement this as inverted dropout, scaling at training time, so inference requires no modification. When would dropout hurt your model? When combined naively with batch normalization. When your dataset is large enough that dropout slows convergence without adding generalization benefit. When you need deterministic outputs for reproducibility in production. How would you use dropout for uncertainty estimation? Monte Carlo Dropout. Run in forward passes with dropout active, aggregate predictions, and use the variance as a proxy for model uncertainty. Useful in high-stakes applications like medical AI or autonomous systems. What's stochastic depth, and why does it matter for very deep networks? It reduces effective training depth by randomly skipping residual blocks, cutting training cost by up to 25%.